So in the last class, we did see that this is actually the construction of the Gregor Muller counter. Let's just have a small brief again. It's basically a cylinder, okay, and you have got two insulating materials here, and in between we have got a tungsten electrode. The tungsten electrode is basically connected via a load resistance to the positive terminal, so that is basically acting as a anode, and the body of this cylinder is basically connected to the negative terminal, so that is acting as a cathode. So from here we can see that the electric field is basically from this anode to the cathode. Within the system we do have a gas medium which is 90% argon and 10% ethanol, okay, and ethanol also has its own application. Why it's there, this is something which we are going to explain, okay. And whatever result we are going to get, the signal, we are actually going to get it converted to a readable form, okay, using an amplifier and some pulse counter and so on. One thing to note here is that in general the idea is very simple. You have some radiations falling on this, and then there will be some kind of ionization happening, and then the electrons will flow from this end, it will complete the circuit and go in here, it will again combine with the ions which are present, okay. So this is basically a very simple idea of the working of a Gregor Muller counter. Many a times it's basically a handheld device, as I've said before. So some of the points to note here is that the Gregor Muller counter was actually invented, you can say, in the year 1928, okay, and the central electrode is made up of tungsten, and as you can see the gas component is argon plus alcohol. So whatever ionization we are talking about will happen because of the radiations like alpha, okay, beta, or even the gamma radiations, okay. So, but the thing is, it can also be used to detect neutrino, but then for neutrino detection, the method is not direct. You know that neutrino is a bit difficult to detect, okay? So the method is not direct. But alpha, beta, and gamma particle can easily be detected, okay? So this is where we start with today's class, where we try to understand that how exactly does it work, okay. So the first thing that I'd like to talk about is the principle, okay. So what's the principle of Gregor Muller count, okay. So the working principle may be a question of 2 marks, okay, that's important. So you can see that this principle is more or less based on something which we call as the ionization, right. So what we have here is the external rays will actually lead to ionization, okay. This is basically going to happen, and then ionization is going to happen of the gas. So in this case we can see we have argon, so the argon will get an ionized, okay, and then as a result of which we will get free electrons, right. So electrons, and we can say electrons will be generated, we can say, okay, okay, and along with positive ions. So it's not only the electron, it's the positive ions. So imagine this, you are basically having a gas, okay, so you basically have some radiation falling on it, let's say some gamma radiation here, as a result of which you will have an electron which is getting generated and also the ion which is getting generated, right. Now you see this is actually a negative terminal, so if you are getting some ions getting generated here, this will actually move towards this edge, so it will basically be more nearer to the edge. So here you will get all the ions, and the electrons, this is the anode, so which is connected to the positive, the electrons will be actually moving along the anode or the electrode rather, okay, the tungsten electrode, the electron motion would be along this particular direction, okay. So this electron and positive ions are subjected to electric field, right. So we can say electrons, okay, and positive ions, okay, are subjected to electric field, right. You are applying a potential positive and negative, so obviously they are subjected to the electric field, okay. And you know, you can actually apply this electric field via battery, so it still works, okay. So GM counter, okay, introduces high potential difference. So you'll basically have a very high potential difference, and that will be more or less direct in nature. So we can actually apply a direct current, and that's nothing but by use of a battery. Okay, and this is good because, you know, in some way it is also advantageous to other counters like proportional counter or the ionization chamber and so on. Okay, it's more handy. That's there. Okay, so we will have electrons now. So at first stage we will have some electrons, and these electrons will actually go and hit other gas molecule, and then again it will knock out some more electron, because these electrons will have some kind of energy. Okay, and this knocking out of electron by another electron will create a kind of avalanche effect. Okay, so this electron, the electrons created leads to secondary electron, right? Secondary electrons as it moves towards the anodes. So you get more and more electrons. So it's simple. The idea is simple. We are basically going to get a kind of avalanche breakdown, right? So you basically have one electron here, okay, and then maybe this will give rise to two electrons, okay, okay, and then these two electrons might give rise to two more, okay, and so on. So this is something which is going to happen, and as a result of which you are going to get a sea of electron which usually basically flows in the system. Okay, so we can basically say that this will actually lead to something which we call as chain reaction. So leads to chain reaction. Okay, one point very important. So the working principle is simple. You have to just remember this, and then you can easily reproduce this in exam. Okay, and we can also say this is nothing but the avalanche effect. The avalanche effect and all is something which you have been hearing about for a very long time, so you already know about it. Okay, and you know there is one more name for this avalanche effect, okay, named after the scientist who actually talked about that initially. Okay, it's Townsend avalanche. So this is the basic principle based on which GM counter works. Okay, but then there are a lot of things that we need to know about GM counters. Okay, so just going to take them one by one. Okay, so what happens if we have got a very large avalanche happening? So the entire GM counter will start discharging, because at some point you're not going to have enough avalanche, right? You're not going to have enough electrons getting generated. Okay, so this is something, let's try to discuss that part now. Okay, so maybe I'll just take this up. Okay, so this kind of avalanche effect leads to complete discharge. Okay, so it is going to discharge the entire tube. Okay, discharge of GM tube. So you might not be having enough electrons here, but then what can be done? Then that is, there is a solution that is done. Okay, what happens is within the system, you know, the electrons will also get decelerated. Okay, there are other processes which are also happening, so let's understand these processes. Electrons get decelerated, and I hope all of you know that if electron gets decelerated, they will result in something which we call as bremsstrahlung. So if the electron slows down in speed, there is going to be some more radiation which is going to come out of it, that is also there. So due to, what is the deceleration reason? Due to the collision with nearby molecules, and this is something which we term as bremsstrahlung. Okay, so I think it's S. So this is bremsstrahlung effect, and if that happens, chances are there that we are also going to get something which we call radiation, UV radiation, and that may be emitted. Okay, UV radiation may be emitted and can travel to other part of the GM tube. The chances are that we will actually get some UV radiation as well, and these UV radiations will travel to other parts of the GM tube. Okay, and there is also a chance that these UV radiation will have enough energy, okay, to actually create other kind of avalanche effects. So it will also create more avalanche effects. Okay, so that is also possible, and create an avalanche effect as well. So you understand this now. So what happens is the electron goes and hits a molecule, it gets into the excited state. As soon as it comes to the ground state, it will emit some radiation, and that radiation would be the UV radiation. This UV radiation may have enough energy to again knock out an electron from a molecule, resulting in another set of avalanche effect that happens. Okay, so you know all these are probabilistic, but then these things does happen. Okay. So, you know, if this is so much of electrons which will be there in the system, this will actually result in the uh, change in potential. Okay, so the discharge usually leads to the change in potential. You need to understand this. Okay, the potential of the entire system will more or less vary based on this discharge that we are talking about here. Okay, change in potential. And then what happens to the electron is what I said just before, that these electrons will start flowing. It will give a rise to a signal here, which is actually a signature that some particle has entered the system. Because if an alpha, beta or gamma radiation enter the system, then only you can get the electrons getting generated, and that will give you a signal which is studied. But then this will actually go and complete the circuit and try to recombine with the ions that was there generated, right? So this is something which we are going to discuss now. Okay, so the idea is there. Okay, so I hope you can understand this. The electrons from the anode will complete, okay, the circuit. So this will basically complete the circuit, as I said. Okay, and it will recombine with the ions on the surface. So you have the ions on the surface because the surface is negatively charged. So it basically have the ions getting attracted towards it. So the electrons will go and recombine with it on the surface of the tube, right? Okay. Create again the neutral molecules. Create neutral molecules. And again it will be set back to another set of reaction. But you know, until and unless a particular set of electrons goes and recombines and creates those neutral molecules, at some point the system or the Gregor Muller counter does not detect any radiation because it has been totally discharged, and that particular point is the time where the system is dead. We usually call it as dead time. Okay, so this is actually a disadvantage of such system, but then this is something which is there. Okay, this is which is fundamental to the system. So the entire process, okay, creates a count. So you understand this. You have the gamma rays entering the system, you get an electron getting created, that electron moves and creates probably an avalanche effect, okay, and then that charge travels to the output across the load resistance, that is being registered. The electron goes back, combines with the surface ion, and then it becomes neutralizes, it becomes a neutral molecule again. So this is the entire process that we are talking about. That entire process will register one count, okay, and takes. So understand this one count, you need an avalanche of electron because you need an enhanced signal. If it's a very signal is very weak, probably it cannot be even detected. Okay, so we do need to detect it, and that's very important, and it takes some time. So this entire process to happen, it will actually take some time. So during this process, okay, this time during the detection, okay, no other particle, so there will be no other particle, okay, which can be detected, okay, can be no other particle can be detected. So you cannot detect any other particles at that point of time. If any other particle is entering, you cannot detect. So exact count of the particle that is there in the atmosphere at a particular point of time is very difficult using a Gregor Muller counter. A Gregor Muller counter can only tell you that yes, there is radiation present, but how much radiation, probably that's not a good device for that. Okay, so no other particle can be detected, okay, and is known as dead time. So this dead time is a very important term. This is not only for this device, some more devices are there which uses this term. Okay, so you please remember this. Okay, so the dead time for GM tube, so if you want to do more accurate calculation, the dead time should be as low as possible, but a GM tube typically has got 200 to 400 microsecond, and 200 to 400 microsecond for detection of radiation is actually quite large. Okay, in that way, that is actually quite large. Okay, so these are some of the important points that I wanted to discuss on GM count. Okay, now there are certain other aspects which also happens. The signal that I detect should only be because of the alpha, beta and gamma radiation which is incoming, and it should not be detected because of any other reaction that is happening within the system. Okay, and for that reason we are using alcohol, ethanol. So this is a very important question I might ask. Okay, so this is something which we are going to explain now. Okay, so there is something which we basically call as quenching. Okay, so quenching is basically an English word. Okay, so if you are thirsty, okay, you can quench your thirst by drinking some water. Okay, so that is basically what is quenching is all about. Okay, so what happens is here, let me just discuss this. The free electron, okay, electrons when recombine, okay, with ion, it will basically create a free molecule. Okay, create a free or a neutral molecule, create a free molecule. But this electron that is moving around might be having some energy which is a bit more. So when it combines and creates a free molecule, the chances are in the process some more radiation might be given out. Okay, free molecule, and it may lead, okay, to the emission of photon. Okay, this is quite obvious because the electrons are making a circle and then finally combining with the ion to create that neutral molecule, but then the electron might have enough energy that after combination, this combination will give out some photon. Now this photon can again lead to a avalanche effect. This photon may again knock out an electron from other molecule present in the system. So this is not because of the external radiation. This photon was created because of the recombination of electron and ion. So this signal that we get in the output is something which is false. That is not because of the radiation. So I don't want this. Okay, and that is why we use ethanol. Okay, so let me just discuss this. This photon, okay, this is what I said just now, is capable of making another avalanche effect. So you can understand that this will actually have a good energy to make an avalanche effect, which we don't want. Why we don't want? Because this is not the signal that I want to study, which we don't want. Okay, so the idea is simple. Okay, so this is something which is not my aim. Okay, what we want to actually study only the signal from the incoming radiation. We want to count only, okay, the external particle and not from this photon. Okay, from the external particle and not from this particular photon. So this is our aim, and this photon, we hope you know that, which is created due to recombination, right? This is due to recombination. This is created due to recombination. So if it is created due to recombination, this is not something which I want. So let's not concentrate on this. So how do we do this? There are certain ways to do it. Okay, so to prevent, okay, this, some methods, okay, like quenching is used. and that is why we are studying this topic on quenching. Okay, this quenching is used. So there are different types of quenching as such. Okay, so there are something which we call as the chemical quenching. Okay, so let's just look into this. Okay, there are two quenching mainly. Let me just list down two of them. Okay, number one, we take up chemical quenching. So in chemical quenching, what happens is, this is what is this done. Okay, ethanol is one of the most common gas. The gas is mixed, okay, some compounds with some compounds like ethanol. Okay, like alcohol. Let's say, we'll just write it down in general. As I said yesterday, ethanol can be written as ETOH. Okay, alcohol like 10% ethanol in this case, ETOH in this case. Okay, so that is what is done in chemical quenching. Okay, what happens is the photon, okay, is given to the nearby molecules, okay, which absorbs the energy. So whatever energy was there with the photon is being absorbed, okay, which this is being absorbed by the ethanol molecules that are present, okay, which prevents we cannot have too much alcohol, because otherwise this original effect will reduce in intensity. The energy which prevents, okay, the additional average, okay. So additional effect due to the photon is basically avoided. Okay, so that is there. So this is one chemical quenching, and one more technique is there, which is external quenching. Okay, so what happens is here the GM counter is usually switched off. Okay, so the GM counter shuts down, okay, for a short period. So if it shuts down, you don't have the potential being applied, so the electrons will combine, it gets shut down, you don't have any potential, you don't have any electron because of the additional photon that is being done. Okay, period of time, okay, and hence the timing is important, at what point it is closed, that is important, and the avalanche effect does not happen, right, does not happen due to the photon. You have the external radiation falling in, you get the electron signal, and the electron combines, they combine, but then it is shut down, so we are not registering that particular signal, okay, due to the photon. So that's that. So this is basically what we call as the external quenching. Okay, there are certain disadvantages, of course, of these GM counters. Okay, so I think by now we already know some of them. Dead time is of course one of them. Okay, but then in general maybe I can just discuss one or two. Okay, let's just write down one or two disadvantages. Okay, disadvantages. So the first disadvantage is very much the dead time. Okay, so we'll just write down, let me not write down dead time, let me write down high dead time. Okay, just a technical term. Okay, so 200 to 400. So you have a lot of questions coming up from this particular topic. Objective question, even explaining GM counter working can be a descriptive question. Okay, so you can always concentrate on that and try to practice it. The diagram is important, some marks will be given for the diagram also. Okay, so it cannot be used for high counting rates. So if there are too much radiation in a system, in a place, okay, and you want to count how much is the intensity of that radiation, that cannot be done or achieved using a GM counter. Okay, and number two, it of course cannot distinguish, okay, between high and low energy nuclear particle. So it cannot distinguish between which is the high energy, which is the low energy. Because once an electron comes out of the system, it will result in giving an avalanche effect because of the potential or the electric field that is being applied. Okay, so sometimes it becomes a bit difficult to know what will be the energy of that incoming radiation. Okay, so these are actually some of the disadvantages that is being we have in case of GM counter. Okay. So I think this is all about GM counter. Okay, I've given you a lot of theory, and it can be a part of a descriptive question. Okay, so I hope you understand this. This is not a complicated system. Once you draw your diagrams properly, I hope more or less you can write it down the right way in your exam. Okay, so let's stop here.